Hello, everyone, and welcome to the Marshall W. Allworth Planetarium. My name is Jessica, and I will be leading your show this evening. You've also met Spencer and Len, two of my students helping out tonight. So for our show, as you can see, we're going to be doing Mythbusters Astronomy. This is kind of a trivia show. We're going to be talking about some common questions and misconceptions and things, and seeing what's real and what's not. If you have any questions during the show, feel free to ask. You are welcome to just ask out loud. If you don't feel comfortable doing that, you can always come talk to me after the show. If you need to leave during the show, you're welcome to do so. You'll just exit through the same door you came in. And yeah, that's it for the moment. So I'm gonna head to the back and we'll get started. All right. Now, as I said, this show is a little bit of a trivia game. So what's going to happen is I'm going to put up a true or false question, and I want you to think on it for a second, come up with an answer. If you want to say it out loud, that would be great. If not, I completely understand. But we're going to get started with probably, it's not my favorite topic, but it's a really, really fun one to start with. So our first trivia, true or false? There is a permanent dark side of the moon. I'll give you a second to think. Okay, you ready? See if you were right or not. This is false. And I very largely blame this misconception on Pink Floyd. But there is no permanent dark side of the moon. And let's kind of take a look at that. So what we're going to do first is head over to the opposite side of the moon that we were looking at, which is dark right now. But let's just fast forward time and see what happens. As we do, you'll see that what was dark side does eventually get sunlight for a little while before eventually being claimed by darkness again. So what I think happened with this phrasing is until we had spacecraft to go to the moon, we only saw one side of the moon. There's only the same side of the moon is always facing us. And let me just reset for this next kind of demo here. So the same side of the moon always faces us. So we always see the same thing. So the far side, the other side that we can't see, is we didn't know what it looked like. So I think it got called dark as in unknown or mysterious. And then that got kind of misconstrued to thinking that it meant literally dark. But what happens is we can watch here, what we've done is kind of blown up the Earth and the moon so they're much bigger scale than they actually are. And as we watch the moon orbit around the Earth, if you watch the kind of dark markings on the moon, you'll see that they are always facing towards the Earth. Now, this leads to a second misconception. People think, oh, well, if we always see the same side of the moon, then that must mean the moon isn't rotating. But that's actually not true. We can see in this kind of example video here, if the moon wasn't rotating, like on the right, then we would actually see all sides of the moon. What's actually happening is the moon is tidally locked. What that means is it rotates in the same amount of time it takes to orbit the Earth. So what happens is it moves in its orbit and it rotates a little bit, and it moves in its orbit and it rotates a little bit. And that one-to-one, that tidal locking, is what keeps the same side of the moon always facing us. So for one last look, I'm going to turn night back onto the moon. And as we watch, you can see that again, over the course of the month, as the moon is orbiting the Earth, all parts of the moon at some point in the month spend about 2 weeks in daytime and about 2 weeks in nighttime. And of course, this is what ultimately leads to the phases that we see, the difference between what's facing us and what's lit up. All right, that was a fun first topic. Let's head on to our second topic. So for our second one, true or false? Astronauts in the International Space Station, the ISS, are weightless because there's no gravity in space. Give you a second to think on it. All right, let's see what the answer is. And in this case, this is once again false. There is gravity in space. What we see as weightless is actually just a perceived weightlessness. They still have gravity. Gravity's still pulling on them. But instead of me going through this, I actually found a really great video, short little video that kind of talks about this misconception and shows kind of why it's incorrect. So let's take a look at that.
Have you wondered what it would be like to be an astronaut floating around in the space station?
But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating?
No gravity.
No gravity.
Zero gravity.
There's no gravity.
The stuff that holds us to the planet when we spin doesn't have nothing.
Gravity holds you down, so in space there's nothing there, so you just float.
There's no gravity in space.
There's no gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So where would the space station fit in this picture?
Can you give me roughly the scale model of the Earth and the Moon? And then we're going to position the space station in there. So about like that?
Closer. About there.
You ready to see the real distance? What do you reckon?
Oh, okay.
It's actually about here. Maybe a little further. I think we were wrong. Now, if the moon is here and Earth is there, whereabouts would you put the space station?
Around here.
Really?
About halfway?
Yeah.
Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. You ready for the real distance? The space station is right about there.
Okay. Close. We look good at this game.
Yeah.
The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra.
But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
Stuff like they float. We've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why? I'm really confused. Well, in truth, the force on the astronauts is almost as much as the force on you. So then, why are they floating while you're stuck here?
The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them.
If the Earth didn't put a gravitational force on them, they would fly into space. Surely. Right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they?
They would still feel weightless until you smash into something.
So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
All right. So yeah, it's one of my favorite things that an orbit is really just falling and missing the ground. So they're not weightless; they're just constantly falling, which is just another, reason on my list for why I don't think I could ever be an astronaut. Because that feeling of constantly being falling, I don't think my stomach can handle that. So, yeah, that's where that term weightless, what it actually is doing, what's actually happening. All right. Well, let's head on to our next topic. So, next one brings us a lot closer to home. True or false, we have winter here in the northern hemisphere when the Earth is closest to the sun. Give you a second to think on it. This one is actually true. We experience winter in the northern hemisphere when the Earth is closest to the sun, and we experience summer in the northern hemisphere when the Earth is furthest from the sun. So let's talk about this. What we're going to do first is kind of get an orbit of the Earth, an orbit around the sun. We're going to make these both bigger so that we can see them a little bit better. Come on. Oh, maybe it's waiting on me. Yeah, it's waiting on me. I forgot that I broke that into two different commands. Okay, so first, let's talk about the first part of it, that we're closer to the sun or further from the sun in different parts of the year. That's because our orbit around the sun, even though it looks very closely circular, is not actually a perfect circle. Our orbit is an ellipse. And so that does mean that at times we're a little bit closer and at times we're a little bit further away. And because of that, people assume that, well, that's where our seasons come from. And that makes sense from what we experience in our everyday lives, right? We know that if we get closer to the fire, it's going to feel hotter and warmer. And if we get further away from the heater, we're going to feel cold. So it's, it makes sense based on our lived experiences. But the thing is, if that were the case, not only would, we have summer when we're closer, which we don't, but the entire Earth should also experience the same season at the same time. And we know that's not the case. We know the northern hemisphere and the southern hemisphere of the Earth experience opposite seasons. So when it's summer here, it's winter there, and vice versa. So that means our distance to the sun cannot be the cause of our seasons. So if it's not the distance, then what is it? Well, what we're going to do here, finally, make the Earth a little bit bigger. We're going to move it around in its orbit until we get to about mid-June. And I'm just going to orient us a little bit better so that we can see this edge on. Now, if we take a look at the Earth in its orbit, oops, wrong way, you can see that the Earth's axis, which we've got our little holes here showing us the Earth's axis, is actually tilted by about 23.5 degrees. So what that means, during June, the northern hemisphere is tilted towards the sun. What ends up happening is the sun is higher in our sky. It's up for longer periods of time. and the sunlight hits at a very direct angle. So you get a lot of energy being hit and being imbued, added, yeah, to the surface of the earth. And so the earth is going to warm up because it's getting a lot of energy. And so it heats up, and that leads to summer and our warm weather. But then 6 months later, when the earth is on the other side of the sun, and I'll turn us to get a little bit better look, you'll see that because of that tilt, the northern hemisphere is now tilted away from the sun. And that's going to give us opposite effects. The sun is going to be lower in the sky. It's not out for as long. And the sunlight, when it hits the ground, is spread out over a much larger area because it's coming in at a much steeper angle or a much shallower angle. And so that means all that energy is spread out more, meaning each bit of earth gets less energy than it does in the summer. And so all of that leads to the earth not getting as much heat, so it cools off and we end up getting winter. And so that's where our seasons come from. They come from the tilt of the earth and the effect that that has on the intensity of sunlight and how long the sun is out for us at different parts of the year. And of course, as you can see, when we are tilted away, the southern hemisphere is tilted towards, which is why we have opposite seasons. Because while we're getting less heat, they're getting more, and so they're going to have summer while we're having winter. This also means that there is kind of an in-between point. Twice a year, when the earth is neither tilted towards nor away from the sun. And that is what we call the equinox. Equinox meaning equal night. That's when we have about 12 hours of day and 12 hours of night. And that signifies our spring and fall. And those are our kind of transition seasons between, our extremes of summer and winter. All right, so speaking of the equinox, our next topic is about that. So, true or false? It's much easier to balance eggs on their end on the equinox. Give me a second to think about it. This one is in fact false. This is an old wives' tale that gets brought up every time in March around the spring equinox. You see this old wives' tale going around that it's a lot easier to balance an egg on its end during the equinox. Now, what I think this stems from is a thinking that if we are not tilted towards or away from the sun, then that must mean the sun is directly overhead. So it's pulling up a bit more than when it's at a different, part in our sky where it would be pulling more towards the side instead of directly up. But here's the issue. Let's take a look at the sun on the spring equinox here in Duluth. It is not directly overhead. In fact, for most of the Earth, the sun is never directly overhead. That only happens for a small portion of the Earth between the Tropic of Cancer and the Tropic of Capricorn, and only for 1 to 2 days in the year. Most other times, it's not directly overhead. So that idea, out. I think the other reason that this wives' tale got spread is a confirmation bias, right? You hear about it, you're interested, and so you try and balance an egg on the equinox, and then you do it, and you think, that's right, it must be correct. But the thing is, that's not a complete experiment, right? If you're testing that it's easier to balance on the equinox, you also need to test on other days. And that's what people don't do. And if you did try it, you'd find that it is equally as easy, or actually probably equally as hard, to balance an egg any time of the year. There's no particular day that it's easier or harder. But I think it's a fun one, so we threw that in the show. All right, let's head away from the Earth and away from the moon and talk about Jupiter. So our next question, our next topic, true or false? Adding a small amount of mass to Jupiter, the largest planet in our solar system, would turn it into a star. Give you a second. Well, this is false. Jupiter is often mislabeled as a failed star. And that's not the case, but we're going to talk about first where this misconception comes from. So, one of the things that leads to this is the fact that Jupiter is made up primarily of hydrogen and helium. And the sun is also primarily made of hydrogen and helium. That's more of just because that's the most abundant things in the universe. So most things are made primarily of that. But because they have such similar makeup, such similar compositions, that leads people to think that, oh, well, Jupiter must not be far from being a star. But let's actually look at Jupiter and the sun side by side. Our sun is about 10 times bigger in size than Jupiter, and many, many, many times its mass. Hold on, I am forgetting the number because it has been a long day. And Lynn, if you remember, please tell me, because I have forgotten. It's a lot more massive. We're just going to say that. It's a lot bigger. There's a lot more stuff there. So clearly, Jupiter is not just a little bit away from becoming like our sun. But our sun isn't the only star out there. Stars come in a wide range of sizes and temperatures and colors. And in fact, the very smallest stars, what we call red dwarf stars, are actually not that much bigger than Jupiter. So what's going on here? Well, it may not be much bigger in size, but in mass, it's at least 80 Jupiters worth of material packed in there. You see, what happens when you have things like gases that really easily compress, the more stuff you throw in there, the more it's just going to compress and squeeze it down. And so you don't get very much bigger in size, even when you add a lot more stuff to it. So technically, yes, we could turn Jupiter into a star if we took like 80 Jupiters and mashed them all together. But as it is, it's not just a little bit away. It would be quite a lot of effort, quite a lot of material to try and turn Jupiter into a star. 1,000 times more massive? Okay, awesome. There you go. 1,000 Jupiters to get to our sun, 80 to get to the smallest of stars. All right, penultimate topic. We're going to head back to Earth once more and take a look at our night sky and ask ourselves, true or false? Stars do not move. Let's find out. This one is also false. I need to put some more trues in here. I feel like it's a little too false heavy. All right, so let's talk about this. When you look up at the night sky and you see the stars and the patterns that they make, as you watch them from night to night over the course of your life, no, you're not going to see much changing going on. But the thing is, just like the sun is in orbit around the center of our galaxy, making a complete circle around our galaxy in about 250 million years? I believe it's 250 million years. All of the other stars in our galaxy are doing the same thing. We're all moving, orbiting around the center of our galaxy. And all of these stars are moving at slightly different speeds. The thing is, they're so far away from us that even though they're moving at extremely fast speeds, we don't notice a difference in our lifetime. But with the planetarium, we can speed that up. So we're going to fast forward here at about 1,000 years at a time. And even going 1,000 years a second, you're seeing a little bit of shift, but not much. So let's ramp it up. Let's go 10,000 years. And now you can really see those stars moving as we're all orbiting the center of the galaxy at slightly different speeds and slightly different orbits. So the starry sky that we see today, the patterns and constellations that we see today are just temporary. And in fact, we know this, and we knew this pretty early on, because humans have been mapping out the starry sky for, well, as long as humans have been around. And so we have thousands and thousands and thousands of years of record of what the night sky has looked like. And you can actually see those changes. In fact, it was the Greek astronomer Hipparchus who first noticed this slight change in the positions of the stars and realized that things were moving. All right, one last topic. It's usually a fan favorite. We're going to talk about black holes. Of course we are. So, for your last trivia question, true or false? Black holes suck everything in. This, if you notice a trend tonight, is also false. There's a lot of black hole slander out there. And a lot of that comes from just not really understanding what a black hole is. So, let's make a black hole. A black hole,
And now for another installment of...
that is not what I meant to play next. We will get to that in a second. A black hole is essentially where you have so much stuff packed into such a small volume that gravity is at its most extreme. Nothing can escape from that pull, not even light, which is why they're black. But the thing is, that's not true all the time. That's only true if you get too close to a black hole and you pass the point of no return, the event horizon. As long as you stay outside of that, then you can escape. So really, black holes are only scary when you get too close to them. And you might think, well, they must be absolutely gigantic in size. And some of them are, but most black holes are what we call stellar mass black holes. So if, for example, we were to replace our sun instantaneously, that's the best snap I've ever done in my life. If we were to replace the sun instantaneously with a black hole, nothing would change. Because the event horizon of a black hole of that size is a couple kilometers in size. You would have to get exceptionally close in order to reach that point of no return. So all of the planet orbits would be fine. We wouldn't get sucked in. Mercury wouldn't get sucked in. I mean, we'd freeze eventually because, the heat from the sun is gone, but that's another story. For something like the supermassive black hole that sits at the center of our galaxy, its event horizon is, I believe, about the size of the orbit of Mercury. So, you're at 4 million suns worth of material packed into that very small area. So again, you'd have to get as close as the orbit of Mercury to that supermassive black hole to be at that point of no return. So they're not these cosmic vacuums that just suck everything up. You're not immediately in a threat if you get near one. It's just if you get too close. Now, of course, this always leads to the question of, well, what would happen if you were to fall into a black hole and get too close? And that is the video. So we're gonna watch that now.
And now for another installment of What If? You ever wonder what would happen if you fell into a black hole? First, some background. Black holes are regions of space where the gravity is so high that the fabric of space and time is curved back on itself, taking exit doors with it. Light is the fastest stuff of the universe. Not even light can escape. Light can't escape. Neither can you. Which is why we call these things black holes. This boundary within which light cannot escape, we call that the event horizon. All the stuff within the event horizon has collapsed to an infinitesimal point at the center. Ready? Here we go. I'm going to fall into the black hole feet first. As I get closer and closer, the force of gravity grows astronomically, but I can't feel it. Because, like anything else in free fall, I'm just weightless. But I'm starting to feel something else. Something sinister. My feet are closer to the black hole, so gravity pulls on them harder than at my head. This difference in force from head to toe is normally tiny, and it goes unnoticed on places like Earth. But in a fall towards a black hole, this stretching force, all you'd notice. If I were made of rubber, then I'd just stretch. But our bodies are made of things like bones, muscles, organs. I would stay whole until the stretching force exceeded the molecular bonds of my body's flesh. At that moment, my body would snap into two segments. That's not even the worst part. Everything of me that ever was gets funneled to the black hole center. So not only have I been ripped in half, I'm being extruded through the fabric of space and time, like toothpaste through a tube. As I keep falling, the difference in gravity continues to grow, and each of my two body segments snaps into two more segments, and so on, splitting my body into ever-increasing number of parts, all the way down to the atoms themselves, and beyond, leaving an unrecognizable array of particles that just a few moments earlier had been me. We have a word for this cause of death. Spaghettification.
And yes, that is the real term for it. It is my absolute favorite science term. If you fall into a black hole, you get spaghettified. So just don't go fall into a black hole, which really isn't a problem because there aren't that many out there and we're nowhere near them. All right, with that, that brings us to the end of Mythbusters Astronomy. I hope you had fun playing along with our little trivia show here. If you have any questions, feel free to come see me at the back. And before you head out, there are some star charts out on the table in front of the TV. Feel free to take one of those with you if you want to do some stargazing later. And yeah, thank you again so much for coming out. I hope you come out to another show and have a safe trip home and a good rest of your week. Thank you.